And with that, I'd like to introduce Peter Braam, who founded Cluster File Systems. He's going to talk to us about the Lustre file system. Before founding Cluster File System, Peter was a professor at Oxford and at CMU and an architect at Turbo Linux and at Red Hat. And I think it'll be interesting to hear a little about a file system that also needs to scale to a great size, but with some different requirements from what we heard about Google File System from Jeff today. So without further ado, here's Peter Braam.
Thank you very much. I have a little agenda here for this talk. I will tell you a little bit about who builds this file system and roughly where it's being used, because I think that gives you a bit of a background. And then tell you a little bit about what is included in a deployment of this file system. And you'll see some similarities with the Google file system and some differences. The similarities, by the way, have a rather simple origin. Many of the people were all working on the same floor in Carnegie Mellon in the computer science department, roughly at the same time. And in fact, there's also another company called Parnassus that builds a file system that's, again, rather similar, and it was also same floor. So I wanted to focus on a lot of issues of scale, and I decided to take you through a tour of scale as, what have we achieved today, what is running today at our customer sites. But our company is actually very much focused on future developments. We get dragged in when people need to break the next scale barrier, and you'll see what kind of people drag us in. And so I'm going to end this talk with telling you about exascale I/O, which is actually really an enormous step forward that is going to take another 10 years to reach or something like that. But people are starting to work on this now. So let me get going. So our company is called Cluster File Systems, which very quickly became CFS, of course. So what do we really do? We basically build and support this file systems. We have a little headquarter office in Boulder, but we're really a virtual company mostly, 6 years old. We've never had any investments, which is quite unusual for small companies. And we're an open source company. It's grown to about 100 staff members, mostly engineers, but as a company grows, you need more and more people that are doing different things. And it's growing fast, but nothing spectacularly fast. Yeah, this is kind of moderate growth, but it's very steady. So we know that there are at least 250 supported clusters. There are probably quite a few more because our partners don't really tell us sometimes to whom they sell. Sometimes the organizations are very secret, and sometimes they just say it's so many terabytes or something like that. We see about 10,000 downloads of the software per month. I don't know to how many installations that ultimately lead. There's a top 500 list of high-performance compute systems in the world. That's the fastest 500. That list gets updated every 6 months. And in fact, it's going to be updated today or tomorrow or something like that. So I'm giving you results that are half a year old here. And we have about a 15% share of that list. But what's perhaps more important is that we run on 6 of the top 10 of these computers. So if you think about really big computers, we have a pretty good hold there on how to do storage for them. And that includes, in fact, the biggest on every continent that has big computers, like the United States and Japan has the biggest in Asia at the moment. That will change soon, I think. And then CEA has the biggest computer in Europe. These, by the way, are the known computers. I think there might be unknown computers, but I don't know about them. As you might imagine, for unknown things. IDC, whom we've never given much money, lists us as sort of the leading HPC, high-performance compute file system. And the interesting thing is that just like what Jeff was saying, things are changing. People don't have one cluster. They have more and more clusters. And we have now several very big customers that have so-called site-wide file systems with a couple dozen clusters sharing this storage. And we're looking more and more at global file systems where people want to go in wide area situations and replications and so on, as Jeff was just talking about. So how do we do this business? It's basically very simple. Partners have picked this up, just like they've picked Red Hat up. And companies like HP, Dell, Cray, and a whole list of actually pretty big companies, they ship our software from time to time and they give us a support contract. But we also have a nice collection of high-end customers. So these are people that make a big investment in storage, like a big national lab or an oil company or a big bank or so, and we have a couple dozen of those customers, and they drive this company forward. So typically our contracts are in fact very, very big. They are not small engagement, but quite big engagements. So what's so unique about this? Well, it's a completely software-only solution. And if you start sniffing around, there aren't so many of these things around. Many of these cluster file systems are tied to hardware. It's open source. And one of the very important things that we have found is it's modifiable. If somebody comes with a new network, we will change the software to support that network. If somebody comes with a different kind of storage box that maybe has no RAID controllers or something like that, we'll change things. We have quite extraordinary network support. Outside of this high-performance compute community, this is not so widely known maybe, but there are in fact lots of exotic networks that are like an order of magnitude faster than what you can get with 10 gig E, and very low latency. And we run over all of these networks natively, doing DMA and so on. That was deemed to be important. I'll show you about performance and scalability. This is, unlike the Google file system, a POSIX-compliant file system. So there's no special APIs. It's not a user-level library. It's just a file system. And it has high availability so that if servers fail, operations continue after a little while. So it scales well. In the same way as Google's file system scales, you just add more servers, and the I/O will parallelize, and the metadata will parallelize further. And so it's built from little commodity bricks, although our customers typically buy more expensive bricks. They don't buy the cheapest servers that Google buys. They buy higher-end servers, but it's the same model. So a good example of the kind of use that we see was at Lawrence Livermore National Lab. They have the biggest computer in the world. It has 128,000 CPUs. It's a beautiful machine from IBM. And in the first week, they created 75 million files and 175 terabytes. The file system is probably closer to a petabyte. I don't know exactly how large it is, and probably pretty full right now. So what you see here is that these files are relatively small. Yeah, this is only 2 megabytes or so per file, roughly speaking. And we have many users with very large files and many users with very small files. So there's not so much of an emphasis on very large files. Although very high performance, you basically only can get with very large files. So the market areas that we're working in are extremely large clusters. A typical partner is Cray, and extremely high node counts. Like the biggest cluster in production at the moment is 25,000 compute nodes using one shared file system. But that's going up very fast. People are talking about 1 million compute nodes in five years, and so it's growing fast. The medium and large clusters, these are things that go from a couple hundred nodes to a few thousand nodes. I would call a 30-node or a 100-node cluster a small cluster. Not everybody would agree with that. So we don't have to modify Lustre for that at all, and our partners take it there. Dell does, HP does, and so on. We often know very little about it. POSIX is quite important there, and high availability is deemed more important at lower scale. If you go to these organizations, they're typically more picky about it. And the third area where we are beginning to be very active is in what you could call very large data centers that are not connected with compute environments, but they're just general purpose large data centers. So you could think about like a big bank, or the military, which has like lots of feeds into all kinds of organizations. And there we are again, I think, being invited to the table for many reasons, like scalability, performance, but also the modifiability, because the large-scale storage problems, they are typically new, and there are typically no real solutions you can purchase. Otherwise, people would do it. Yeah, there's still a lot of people walking in. So how does Lustre work? They've all come just in time. Now we're talking about real things here. So Lustre has clusters of typically commodity computers. You will see 3 types of computers in a typical cluster. Lots of clients. These clients may or may not have disks, but they see this global file system. They can use it as the root file system. They sometimes do, but typically they use it as a data file system. And it can be, from one client to hundreds of thousands of clients. It varies a lot. There is a group of metadata servers. And the metadata servers handle everything related to file names and location management and those kind of things. Protection of files is largely handled on the metadata servers. And metadata servers have disks. Yeah, they need disks, and typically these are RAID arrays. And then there are so-called, what we call object storage servers. You could also call them I/O nodes. And whereas there might typically only be a handful of metadata servers, like 1 or 2 per file system, there are very often hundreds of I/O servers. And these do the file I/O, as you may imagine. And there are lots of different companies shipping different kinds of I/O servers with Lustre. Some people have just little Celeron boxes with a few disks in them. Other people buy EMC RAID arrays, yeah, and there's just a great variation. In some cases, it's software RAID that we use in Linux. We had to change it quite a lot before it worked well, but and in some cases, it's expensive RAID controllers that other people supply. So there's just a great variety, and that's the beauty of this. It's just software, yeah, but the integration tasks are not to be underestimated, yeah. It can take a lot of work to get a new kind of setup working really nicely. So how does this work? Clients do file opens with the metadata server. Yeah, that's the most important thing with I/O is you open a file, you start reading and writing to it. So you go to this metadata server and you say, give me a file handle for that file. And a lot of information comes then to the client, and the client starts doing file I/O and file locking with the I/O servers, the object storage servers. This is a simple model, and it parallelizes because there are lots of object servers, so the I/O, which is usually the bulk of the load, can be handled by many servers and scales very well. But when you do things with multiple servers, you introduce very complicated problems, because if a file has a little bit of data on the metadata server and then all its file data on other servers, just imagine what can happen when the power goes off. You can be left with a piece here and a lost piece there and that kind of stuff. And you have distributed recovery, which is a very complicated problem for which, in particular, efficient algorithms are fairly hard to come by. Yeah? And I will show you how we have solved most of those problems. So here is typical layout of a file in Lustre. We call something a logical object volume, so we virtualize all these devices so that we have a simple API. You say, you know, you open an object, and in fact, it stripes over many servers. And here you see one object that is striped over 3 servers. That's the white object. And you know, so that grows from 1 to 2 to 3, and it will wrap around. And the wrapping around is shown in the orange object. Yeah, and so you could, for example, imagine that a company is rendering movies, and this is actually happening quite a lot with Lustre. Harry Potter is special effects of Harry Potter use this kind of model. They write little frames of the movie for the file on many different servers, and it forms one file. So there are lots of holes in the file because, you know, one frame takes longer to render than other files and so on. So it's from a POSIX file, it's usually quite a complicated file. How do we implement these objects, and how do we implement the metadata server? It's just Linux disk file systems, although we're about to come out with a Solaris version on CFS, because CFS is a very beautiful file system. But everything here is just stored in ordinary, we call it LDiskFS files. It's really ext4. We do a lot of development on that file system, and I'll tell you more about that. So if you took a Lustre cluster apart and say, hey, let me look at these disk partitions, you can actually mount them with ordinary file systems. You could say, boy, a lot of strange files here. They have numbers, they don't have names. And then on the metadata server, you would actually see the file tree, but you wouldn't see any file data. Yeah, you would see a lot of strange extended attributes that contain the, you know, the pointers to where things are. So the capacity and the scalability features are very similar to what I just heard from Jeff. Petabyte file systems. Today, clusters go up to about 100 gigabytes per second, and 25,000 clients. That's the sort of scale that we work at today. So we support 10 different networks. So of these 10, I think there are 4 different versions of InfiniBand networks. The industry does have great difficulty to reach standards, is my impression. Yeah? So there are 3 different InfiniBand companies, and they somehow managed to get 4 versions of software, where, of course, one of them is supposed to be open, but you can't make money with open software, they say, so that one isn't used everywhere, and so on. We route between these different networks. So it's possible with Lustre to have like an InfiniBand cluster on one side and another InfiniBand cluster on another side, and they can talk to TCP or some other network with routing software. And strangely enough, this becomes very important when you have many clusters because it's difficult to grow these expensive networks. You may be surprised to hear that half of our code is networking code. And this is needed to get not just rich features like routers and many network supports, but also for high efficiency. To get something like 90% out of a GigE pipe is quite a lot. Yeah, a GigE pipe actually doesn't max out at 100 megabytes per second. It's 125. Yeah, and we have a lot of code, but we actually can get up to about 118 out of 1 gigabyte Ethernet link. Yeah, and that has grown this network code to be very substantial, but valuable for us. Many people like to play with different networks. I think the rest I've already said here. There is advanced security. Lustre is just about to come out a version with Kerberos. You can find some betas on the mailing lists, I think, and there's going to be file encryption and audit logs and so on. There are lots of people that want that kind of stuff. So scalability is the theme of this conference. So until today, we've mostly been capitalizing on growing the object server pools for I/O scaling. And this is very similar to the Google file system. Yeah, you get more and more servers, you can do more and more I/O, you get more and more capacity. And it's served us quite well, up to hundreds of servers, and petabytes of storage are possible with, these days actually not so many servers anymore. With a terabyte disk, it's only about 1,000 disks to get a petabyte. Yeah, that sounded very far away. And 1,000 disks, they fit in maybe 10 racks or something like that. Yeah, so that's a good room full of machines, but it's not something that you can't imagine anymore. But as you will see, there are many problems lying ahead that lead to new scale. So scalability 2 is metadata clustering, and that allows us to grow the metadata operations many more. There isn't a huge demand for metadata operations at an enormous speed. You will see that so yes, there are demands, but we can get pretty high numbers today, and the numbers that people are asking for are actually relatively easy to achieve. Not thousands of metadata servers, but just a few hundred will carry us forward for a very long time, it looks like. On the other hand, there is an interesting challenge out there. There isn't a single clustered file system yet that has put through like 1 million file creates per second. Yeah, just to give you a feeling that's a problem that's not solved at the moment. And the problem is I can solve it, but I don't have the dollars. You need to get a lot of kit to do this. So I need to persuade a customer to say, we'll do that for you. And they do sometimes. So scalability number 3 is to move into the wide area multi-cluster arenas where there are multiple clusters talking to each other. Some will be proxying for each other. And another very important thing is that typically people will organize very carefully managed migration. So I worked on the Coda file system, which had all these ideas. You can use it everywhere, disconnected and connected and so on. And you got lots of conflicts. This was a big problem, yeah, that people would update things on a laptop and then on the desktop, and it banged against each other. People know that, and they are avoiding it like the plague. And so they do a lot of management surrounding replication to do that very carefully so that they stay out of trouble. And so that's something that we're very active with at the moment to get more and more software to help these problems. It sounds very similar to what Jeff said again. So let's start looking at scalable I/O, and then I'm going to tell you a little bit about scalable metadata and how we deal with recovery, because recovery is such an interesting problem and it's talked about so little. And then we'll go further with wild talk about large numbers. So here's an example of a problem we were working on in 2004, I think, or late 2004. We were asked to deliver a fast I/O server, and here you see some graphs of an ext3 or ext4 file system these days, and we're writing to many files in this with many threads. So the horizontal axis shows you how many threads are writing, and then the colors show you how many files you're writing. When you're writing multiple files, it's actually very hard to get good I/O, and I will show you several examples. These numbers, so this array can do about 1.2 gigabytes per second, so it's a little fridge with fiber channel cards and things. And what you see is if you write one file, you can get very good reads. You see that on the right top, yeah? You get the full bandwidth, and the moment you start dealing with 2 or 3 files, it goes to hell. The cause of it is shown in the left bottom. The SCSI request sizes that you got out of the Linux kernel are miserable. Yeah, the Linux kernel is extremely good, was extremely good at taking large IOs and breaking it up into small IOs, which is exactly the opposite of what it should be doing. Yeah, this was largely fixed in 2.6, but a few years ago we were actually fixing fiber channel drivers to not do this. Very strange that nobody had looked at this. Here is how we reworked the block allocator, which is now in ext3. The allocator had to become very thread sensitive to avoid intermingling allocations. And this is the kind of thing that feels reasonably confident. Yeah, you see curves of things lying on top of each other. If you write 100 files or one file, it doesn't really matter. You get more or less the same bandwidth. This work actually led to a very beautiful system. It was delivered to an organization in France that builds nuclear weapons, but also helps industry do simulations for software. It's called CEA. And they have 40 servers from a company called Boole. I didn't even know that Boole still existed when they first called me, but it was the same company, and they're actually still building quite beautiful server machines. And so they have 40 servers only, each doing 2.5 gigabytes per second. So they put 2 of these RAID arrays behind them, 24 fiber channel cards per machine or so. These are not cheap little boxes. And they get about 100 terabytes per second out of that system. Yeah, so 40 servers, and they have something like 8,000 CPUs or so in that cluster, but also in very big fridges. So it comes in units of 64 or something like that. It's an IA64 system. The networking in this cluster is also very interesting. It's 3 strands of an exotic network called ELAN. Each strand is about capable of 1 gigabyte per second, about 800. And so with 2.5 gigabytes per server, you can see that we're doing very nice plumbing. The pipe into the server and the pipe out of the server is all equally large. Yeah, and plumbing is very, very much a part of architecting good I/O systems. Yeah, if you have a network pipe that's too thick, you're just wasting money probably. Yeah, and so we do a lot of little calculations on envelopes. Well, there are no envelopes anymore, but looking, how much bandwidth does the disk have, and so on, and then match that up. So in 2006, we got attacked by some customer that said, we're writing a lot of small files and it's not working terribly well yet. And so we started to work on yet another disk allocator for ext3 or ext4 file system. This one is not yet in the kernel, but it will probably go in pretty soon. And this is all about writing small files. So these people had literally tens of thousands of nodes writing small files, meaning like a few K. Of course, what you'd really like to do is buy a whip and go after the application developers and tell them, don't do this. Yeah, but that's not the way the world works. Yeah, they're your customers. You can't hit them. You have to do small I/O instead. Yeah, and it's very time-consuming. A lot of engineering went into it, but the results are very beautiful. I'm very, very excited about it. So I'll show you what happens. So it actually turns out that small files suffer from seeks very badly. So they don't really need a lot of tree structures and so on to look up. I was prepared for all kinds of big misery dealing with small files, but if you just pack them closely on the disk, our file system developers in the company discovered that the I/O works very, very well. I don't know if I'm saying this here. So Hans Reiser is, of course, extremely well known for building file systems that do very good small file I/O, but his secret is much simpler than his solution. The secret is that he put them all very closely together. He didn't need these very complicated trees, I believe. Yeah, he could have achieved the same results with just tight packing as we now do in ext3. Here's a couple of graphs. And this shows you again how engineering helps. And this is a very interesting graph. dbench is a benchmark that simulates a Samba server. So it puts a load on a file system that's extremely similar to a Samba server. And many people run dbench 1, 2, or 3, which means run 2 or 3 threads. And it always works so beautifully. It works actually very, very beautifully until you sort of hit 8 threads. Then it's beginning to show sign of pain. If you run dbench 64, several of the file systems will crash immediately. Machines become completely irresponsive. And the throughput becomes a complete disaster, typically. And so here you see how very famous file systems, like the XFS file system, has excellent dbench throughput if you just use a few threads. But if you hammer on it with 64 threads or so, you see that the throughput almost becomes nothing. You can see that the ext4 allocator is a big winner here. This has a lot to do with multi-threading and allocation. By the way, the file sizes of dbench are a mix from about 4K to a few hundred K. The largest files in the benchmark are a few hundred K. So they're what we would call quite small. Probably if Hans Reiser was here, he wouldn't be very happy, because this isn't what people are seeing normally. And you can argue this is not a load that the Linux community is very interested in, but my servers run, in fact, usually more than 64 threads, sometimes a few hundred threads, and so it's very similar to a server load. Here's another set. So here, by the way, I think this is in seconds, so higher is worse here. And there are two things. One is unpacking a tarball. It's a Linux tarball, which of course is the canonical tarball in a company like mine. And so untar the thing and then remove it again. And what you can see now is that ext3 and ext4 are hugely different. So that's the different allocator, and at least for removing. And the file system actually kind of par. The riser and the ext3 with the new allocator, they're doing pretty well. This is one of the reasons we've stuck with ext3 so far. It also has a very good file system checker. That's very well known, of course. It's a very reliable file system, but I can tell you one big disaster we encounter with ext3, and I will do that later in this talk. The end of this is in sight. So here you see a graph that is an interesting one. This is from a computer called RedStorm. It's used in a national lab called Sandia. That's in Albuquerque, New Mexico. RedStorm actually doesn't run Linux, so we had to port the file system to some microkernel operating system. And this is a machine with very many clients. It has 25,000 clients, and they did a test here with 10,000 clients. So what you see on the horizontal axis is what happens with the I/O when you have more and more clients joining. And there are two graphs. At the top, it shows you where every process is running. Every node has its own file to write to. And the bottom is where the entire cluster is writing to one file. That sounds pretty exotic, but it actually happens. So it's 10,000 people writing in one file. And so there are actually very interesting things. Like, first of all, it's not great, because it isn't a very constant graph. Also, if you don't have a lot of money, you might be very concerned that it takes 2,000 nodes to reach full speed. I mean, that's kind of absurd, but I don't know what the reason is. It probably has some kind of weird reason. What we learned from this actually was that the arrays were misconfigured. So they had set them to do a lot of read-ahead. And read-ahead is great if you have a desktop machine. It's not great to have 10,000 machines trying to do a read-ahead, because there isn't enough memory anyway. And so why are you doing read-ahead? And so integration issues left and right. It also turned out that if you look carefully, the top graph hovers around 40 gigabytes per second, the bottom graph at 25 or 30. And it turned out that they had hooked up the disk arrays in the wrong way. They should have used logical volumes to use more of the fiber channel connections. So the single file, for some rather silly reason, couldn't get the full bandwidth. Integration issues, so it's kind of annoying that basically the software can do it, and it's still very, very complex to get something like this together. When a machine like this is put in production, it costs $100 million roughly. They are not giving the file system hackers much time to play with this. They immediately want to start doing their computations, and so the jobs are typically very rushed and somewhat compromised, and I think different organizations have even more demands than others. Good. So when you start looking at extremely large file systems, there is a problem coming up. So if you have a petabyte file system and you have 500 gigabyte drives, very common kind of configuration today, you have 2,000 disks or something like that, and one disk will blow up pretty quickly. And the estimates vary. It's really very interesting how much they vary. The manufacturer will say 12 days between disk failures in a cluster like this, so with 2,000 days. I was in a pessimistic mood when I gave a talk, and I said, well, I think it's 10 hours. It actually turns out that, which is very different. I was much closer than the manufacturers to the reality. We asked a customer that had this kind of configuration, and they came up with something like 30 hours. And by the way, there is indeed a trend that disks break in the beginning, then it gets better, and then it gets worse again, and so on. So new clusters are vulnerable for breakage, and then it's a bit better, and then older clusters are vulnerable. But double failures will start to happen quite quickly, and this is a problem. So the other thing is that at the moment, Linux file systems, disk file systems, many times, and maybe XFS doesn't, but ext3 has some kind of limit on the number of terabytes in it, and we've tried to remove that. And it's now 8 terabytes or so at the moment. It used to be 2 or so, but there's actually a whole load of bugs left and right in the system, and if you want to push that up to like a couple of petabytes or so for a disk file system, it's not possible. So there's lots of limits. There also can only be 4 billion inodes per file system, and customers are asking me for 1 trillion inodes. So I need a lot of file systems, and I prefer to have bigger file systems. So things really need to be done here. But the most important thing is that this hardening problem has to be done. So if you have a RAID controller blow up that has a big cache, or if you have double disk failures or something like that, you need to check your file system. And checking a couple of terabytes of disks takes hours and hours, and we have actually made speed up improvements to FSCK, so it goes like 5 or 10 times faster now, but that's still not enough, It takes hours and hours, and you have no access to some files. That's the best possible situation. In the worst possible situation, there is no file system, If the metadata server needs to be checked, it's very, very bad. So ZFS is a file system from Sun. I've seen a lot of beautiful research, and they put it really well together. It's always possible to find some, to be critical about it and so on. But it's actually very, very beautiful. I think it will probably be ported to Linux, but it will take an incredibly long time. It took years and years to get XFS really stable, and I don't think that ZFS is going to be stable. And there's licensing problems, and God may know what. So there's another approach to this that says, it started at University of Wisconsin. They called this Iron ext3. And the way you start protecting your data is to add little checksums to everything. So your CPU usage, which at the moment is almost 0 on these I/O nodes, it will shoot up, Because just imagine that you get a gigabyte of data flowing through a server. You have to start to check all kinds of little bits, to make sure that you know if the data has integrity. And that's, by the way, also what ZFS does. So the approach that Wisconsin proposed is, I think, also very attractive, because they proposed a lot of little fixes so that every time you make a small improvement and you reduce the chance of checking. But unfortunately, this problem is so important for us that we will have to jump on both bandwagons. We will work with ZFS servers, maybe with OpenSolaris, or maybe we'll help with porting it to Linux. And we will help ext4 get further. It's just we are in this business of large file systems. We have no choice but to help. So many people start asking us, so what about a 1 petaflop system? So at the moment, the fastest computer on the world runs at about 300 teraflops. That's with 128,000 CPUs. Everybody is now talking about petaflop systems being delivered in 1 or 2 years. And so a petaflop system wants to get about 1 terabyte per second of I/O. So that's a little bit more than 100 gigabytes. It's only a factor 10 more. So we have quite a good story here. We have servers that do already 2 gigabytes per second. We also have clusters that have 500 I/O servers. And so if you multiply these two numbers, that system will do a terabyte per second. It just so happens that at the moment we have no customer that has so many very big servers, but there is a way out here. And so the other thing is that the number of clients that we handle at the moment is 25,000, and the number of cores is jumping up very fast, so the number of clients is not going to jump up very fast for a petaflop system. So for once, this doesn't happen very often, we are very confident. The petaflop systems are not a problem for us. We will deal with that without much difficulty. Good, so let's look a little bit at metadata. This is a very short example. So metadata in Lustre is really very clustered. So for example, we can store the name of a file on one node and the inode for the file on another node. Yeah, so we really tear apart file systems there. And here is an example of how you make a directory. So a make directory will go to some metadata server, and then that metadata server may say, oh, I put the inode somewhere else based on some kind of a policy. And so it's a complex system to place metadata. And in this way, you can get very nice load balancing because you can, for example, place the metadata based on the hash of the name. And this is a very old thing that comes from the VAX days. Yeah, so you compute the hash of the name, you pick your metadata server, and that's where you go. Or you can say, I do it based on the network ID of the node, so that nodes get locality on their metadata servers. Or you do it based on the user ID of the user, so that users get locality on metadata servers. Yeah, different policies probably have different applications. Yeah, and we've already heard of many different proposals for using this or that policy. So here you see a simple example of some metadata testing with doing a stat, so you get the attributes of a file, the file size, and so on. And this is in a collection of rather big directories, starting with 1 million files to going up to 10 million files in one directory. You have to make, by the way, some changes to the Linux kernel before 10 million directories works well. Machines freeze for reasons that are not so very interesting, but important. It continues to surprise me why people ask us to do these things, because you rarely ever hear. Actually, do I have time for a little joke? Yeah, I do. So the first accident with million file directories is actually really worth telling you about. At Lawrence Livermore, somebody had not cleaned up his data, and he created more and more and more files, and actually built a directory with 2 million files. Nobody knew about this. In most cases, people would know about it because it would stop working. Yeah, but it didn't stop working, and so there was this 2 million files. At least it didn't stop working until I tell you what happened next. So the RAID controller blew up, and these RAID controllers, these guys have no money, so they buy cheap RAID controllers, and so they leave the file system in an inconsistent state. By the way, this is 2002. I promise you that what I'm about to tell you will not happen today. So they use FSCK, and FSCK had a check. It said a directory bigger than 32 megabytes must be completely corrupted. And it said goodbye to 1.8 million files in one blow. Zoops, they were gone. And so the file system was actually pretty healthy, but the files were zapped out. They were all temporary files that should have been cleaned up anyway, so we did that very efficiently during the file test. Anyway, the interesting thing about this graph is not so much that it scales if you get 1, 2, 3, 4 metadata servers. The other thing that you see is distributed caching. You see the knee in all of these graphs. Yeah, disks are dog slow, and so once you run out of cache, you will go down very, very badly. Yeah, there is no answer. There is 20 millisecond seeks on disks. Yeah, and so the knee goes up quite linearly too. Yeah, and that's nice because that means that a load can actually be helped very much by memory in the whole cluster. Okay, a few slides about recovery. There are lots of problems with recovery. Disk file systems need recovery. Our servers do very few things synchronously. So when the power goes off, they roll back, and the clients will replay the stuff. So that's a big problem. Open and maybe unlinked files may need to be reopened. But the most interesting problem is perhaps these distributed problems. So we have files, and then we have what we call the objects, which are the pieces of files that contain the data. And as I said, you can lose a few of these and be left with some half-finished kind of file creations. So recovery always aims to restore a globally consistent state. And I'm going to show you a few of the mechanisms that we use. I think some of these things are a little bit original. They're so simple, it's hard to believe that they are original. So Lustre has a request protocol that's quite different from other network file systems at the moment. We make a request, like make a directory, and we immediately get a reply. Directory is made, here's the inode number and so on, whatever you want from that reply. But the client is aware of the fact that this may not have hit the disk yet. So it keeps the request to replay it. And so there's a second reply coming called the commit callback. And that's actually drawn here as the 5th step in the thing. I will come back to the other one in a moment. So file systems and also databases, strangely enough, don't have a hook normally to tell you what you did in memory is now on disk. We call that the commit callback. We added it to the file system so that we are told when things commit so that we can stop keeping this replay information. And this keeps the possibility of keeping limited amount of replay operations and discarding it at the right moment. And that's the foundation of our mechanism. Now, there is another very important thing. We are using clients to replay state. And it's sometimes very important that we know that the client has the reply, because if the client doesn't have to reply to a request, maybe it can't rebuild the state for some kinds of requests. And so, very funny networking issue here. We have reply acknowledgements for certain requests, and they are needed to avoid a problem called cascading aborts. It's a known problem in databases, but it's not normally used in this kind of setting. So this gives you a picture. So I'm going to skip over one of the. I just talked about this slide actually, so there's nothing new here. I can tell you that there are a lot of problems at large scale. So I'd like to actually talk here about two things. So if a client goes away for a while and it comes back with a lot of cache data, maybe unfinished operations, what do? You need versions. You need to be able to say, well, nobody touched this thing, so I can still dump my dirty data onto this file, yeah, and I'm sure that nobody else has touched it. Funnily enough, file systems have no versions, yeah, so ext3 has no way to tell if a file really changed. Yeah, a 1 second granularity of an A time or so doesn't do it. Yeah, you need exact versioning of things. Another thing that is very interesting is timeouts. So in busy clusters, big, large clusters, the timeout mechanisms that all RPC protocols have, they simply stop working. And we see that I/O in a busy cluster can take 300 seconds to complete for a simple file write. There's nothing wrong with the clusters, nothing wrong with the file system. It's just that everybody is wanting to do I/O. Yeah, and there are thousands of requests backed up on these servers, and it just takes a little while to get through them. But a timeout value of 300 seconds is indistinguishable from a complete failure. Yeah, people get irritated, they walk away, they hit Control-C, and so on. So you need adaptive timeout, yeah, so that in normal situations, the system will very quickly detect the failure of an operation, and in other cases, people kind of know they have to wait, yeah, and so adaptive timeouts is complicated because you have to send extra messages. Good. I'm going to skip this diagram because it's kind of a long thing to talk about. I want to finish this talk talking about exascale because it's the next thing to come, and it's nice to do things with big numbers. So at the moment, the US government is calling lots of meetings left and right to discuss exascale computers. They're targeting these for 2015 to 2020, so about 8 to 10 years from now. So if you look at this today, you would be looking at a machine with 250 million cores. My house is in Canada. That's 10 cores per member of the population. Yeah, so that's this computer would have more compute power by an order of magnitude than Canada, maybe by 2 orders of magnitude. Yeah, and it's pretty interesting how many cores this is. It would be about 2 million CPUs, a couple hundred cores per CPU. Yeah, in a few years' time. Maybe about 500,000 client nodes. That's 20 times more than we have today. Maybe not so bad. Yeah, we have 10 years' time. But maybe we can be lucky. Maybe the clock speed will still go up a factor 10. Yeah, clock speeds are no longer going up very fast. And then if we had 500 cores per socket, the whole thing would be back to the scale of today. You know, 10,000 clients. We know how to do that, more or less.
Megawatts.
I don't do energy, but maybe it's reassuring to know that many of these machines run in nuclear weapon labs, so they can generate energy, but maybe not very controlled. So the file system characteristics is that the minimum bandwidth that they want to look at is 250 terabytes per second. Terabytes per second. Yeah, this is, so this is 1,000 times more than what we're toying with today. And the reason is that they want to dump the memory of the machine, about 40 petabytes of memory in this cluster, to disk in about 5 minutes. That's the current framework of compute applications. There's a lot of data memory. It needs to hit the disk in about 5 minutes. And the funny thing is, the disks are not the problem. there will easily be 10 terabyte disks, and so having a couple of exabytes of storage or so, that's not the problem at all. But the next issue is the bandwidth of disks is a disaster. Yeah, it is not going up very fast. At the moment, a disk bandwidth of a good disk, a good SATA disk, about 50, 60 megabytes per second. If we are very lucky, it will go up to 250 in 10 years' time. Yeah, but that's really challenging because there are problems ahead in the disk industry. And that means we don't need 100,000 disks. We're talking about 1 million disks. And 1 million disks is a lot of disks. So this is a problem that I think is not so easy to solve. And compression of data may help. And there are a couple of other things that people can do here, like staging the data. So I want to tell you a few other interesting things. So this slide we've already talked about. Disks are going to fail so fast, 200 disks per day. Now, that's perhaps not a problem. There are libraries with 5 million books, so why couldn't you have a computer with 5 million disks? Yeah, the Harvard Library, I think, has 5 million books, so we just need to take librarians and send them to SysAd courses, and then I think everything is maybe well. But we need very good software to manage disk failures. At the moment, many disk failures result in a disaster, even with very expensive vendors. This is not so widely known, I think. EMC doesn't tell you these things, or no vendor will say, oh, if a disk fails, you have an 80% chance that your array doesn't come back. It's not 80%, but it's probably something like 8% or 10%. If you have 200 disks failing per day, we need very good software. The other interesting thing is, currently we're using RAID technology from the 1980s. RAID 5 and RAID 6 is Stone Age stuff, and there is actually much better RAID from the 1990s. That's an order of magnitude faster to build. It's called parity declustering and so on. And maybe there is a solution to the RAID problem. I'm not so pessimistic about this. And we already talked about integrity issues. Yeah, we need checksumming, end-to-end verification that the data is correct. Metadata performance is not a problem. There will be 50 to 500 million cores in a system like this, so we need to be able to do 50 to 500 million metadata operations. All of these cores will want to create a file. But today we can already do 1 million metadata operations, and you don't need very many disks for this. You only need like 100,000 servers for this, and so I have the feeling that it will probably just scale over 10 years' time. Yeah, it's not like a few orders of magnitude out. It's just like 1 or 2 orders of magnitude out. And today, for example, the Blue Gene L machine at Livermore creates 128,000 files, and they're complaining to me. They say it takes about a minute or so, and it's 2,000 files per second sustained on a relatively simple server, just one of them. Recoverability is something we just talked about. At this scale, this is like internet scale. This is really very, very similar to having a city with computers, a big city. And so there will always be something wrong in your network. There will always be servers blowing up and clients blowing up. So you really need, at the file system level, to have restartability. If something didn't make it, you want to just be able to send it again and it goes through. Unfortunately, standard Unix semantics is not the right thing for this. You need some small changes to this, like versions and so on, to really know, was this done already or not? And if it was done, what was really the result? And so, so that's very important. Another thing has to do with congestion control on the network. If you don't do resource management well, you will get lots of stuff on the network that you don't want on the network. So that I have a slide about that stuff here. So quality of service is going to be very, very important in a cluster like this. You don't want to have accidental bottlenecks. If you in a large-scale machine or in a city, basically, if you make a mistake with resource management and you send suddenly, millions and millions of requests to one server, you have a lot of problems for end users. All these clients will have to wait or crash or something like that. It's not going too well. So negotiating where are the bottlenecks is going to be very important. This problem is very different from the internet problem because it's a read-write problem. It's not a mostly read problem. It's mostly writes, in fact, that need to be managed very carefully. So I think there's going to be a lot of exchanges in networks to decide which servers are relatively empty. Let's put the data there because they have the bandwidth and adapt that as the load varies in the cluster. But networks are very fast. Disks are very slow. So making these networks protocols richer, I don't think is a problem. It's the disks, you don't want to write anything that you don't have to write because they're so slow. I have a little roadmap here, but that's probably best left. So here you kind of see that in 2014, we hope to have an exaflop system. You see a lot of steps along the way that I've talked about. Yeah, in 2009, I think there will be wide area clusters coming. And right now, we're sort of going into the petascale. I think I have a few minutes left for questions, so I want to stop here. Yeah. Go ahead.
What's the metadata store data structure?
What is the metadata data structure? It's actually a standard file system. But we shifted the root into a subdirectory because we also need a pile of administrative files. So you can do ls there, and you see almost everything that you expect to see. And the remainder that you don't see is in extended attributes, but they're standard extended attributes. So it's at the moment we do it with completely standard file system.
So every file accesses a sequential scan in those directories?
No, it's all hashed and so on. So there are a lot of changes in that file system. So you look up by hash values, and then you find the inode. Usually the extended attribute is in the inode and so on. So you get it in memory in one blow anyway.
So it's effectively hash over files?
It's hashed over files, yes, that's right. Yeah, and no more disk accesses actually typically than writing in a local file system. It's not, there isn't a lot of overhead. Yeah.
I see that in the frequently asked questions you said that OS X is going to be supported in 2005.
I expect in 2005, that is a print. We actually got pretty close to having one on in 2005, but it's going to be next year, I think. There's now a customer paying for this. So the question was, is OS X going to be supported? Yeah, the client for Apple. There aren't a lot of Apple computers out in this community. They're kind of expensive, but there are some. Yeah. Maybe one more question. I think then we're probably beginning to run out of time. Yeah. Go ahead.
Do you see the transition to flash-based hard drives?
Do I see a transition to flash-based hard drives? A lot of people are talking about these drives, of course. They're very expensive still. Yes, if the cost comes down, there will be a transition. And the attractive way to use this is as a nearby cache in conjunction with compression. So put some flash right on the motherboard, maybe related to a compressed size of half of your RAM or so. Yeah. So if you could compress half of your RAM, then that would be a good amount of flash. That would help tremendously. Yeah. So that's talked about a lot, but it's too expensive at the moment. Yeah. One more then. Yeah. Go ahead.
Are all of your customers sequential bound? And everything you talked about is all sequential access bound rather than random I/O bound.
Most of my what are my customers sequential bound? Actually, they're not. The big numbers are all for sequential I/O. I can tell you that most of my customers are bound by clearance issues, and I have no idea what they're doing. Yeah, and nobody in my company has clearance, and if so, I don't know what they do, but I think the load is very varying. The good numbers come from sequential stuff.
Yeah, I actually don't. Right, that's what I was after. I'm interested in seeing how do you deal with the random I/O problem, because that's a hard one.
The object storage servers help tremendously with random I/O problems because you have so many of them. You get an enormous amount of seek operations, and Lustre can easily beat NFS on small file operations, for example, because it just has more servers. Yeah, how could it not? And in fact, it also does fewer network transfers. Yeah, but at that point, there may be some other optimizations like more group commits and so on that would help. And we will be doing quite a lot of work on this stuff. Yeah, so it's. That's also somewhere in this roadmap. Maybe we can take this up in the corridor. Yeah?
All right, Peter, thank you very much. That was pretty exciting.